All right, and welcome to Algorithms Live. Uh, in this episode, we'll be covering this technique for exchange arguments. So it's going to mostly be proofs, but we will do some live coding in this episode. I'm going to be coding a problem. But before I begin, a little bit of housekeeping. So for those of you that don't know, TCO starts tomorrow. Really excited to see TCO starting. This is actually the first year I've ever secured a first round buy, so I don't have to compete in round one, but I'm still excited to see the problems and want to do that. There's also a TCO regional event this year in Austin, Texas that I'm going to be attending. So if anyone else is going to the regional event, definitely say hi if you see me there. I love to talk to people. The other cool thing is 2 weeks from now on a Saturday is we have NAIPC for NAIPC 2017. So if you haven't already registered for this, you can go to naipc.uchicago.edu. And so anyone looking to train for World Finals, these sets try to approach World Finals level difficulties or try to get close to World Finals level difficulty. So if you're looking for something hard that hasn't been seen before, training for World Finals, that's where we're going for with this set. There's an open division. So there's open division for the US where there's prizes, US and Canada. So just North American open division. And then there's also an open division for the rest of the world. So anyone that's interested in these type of events can compete. And so I guess the last thing is I mentioned on the blog that I'd be covering this problem of split the sequence. And when I was preparing today's exchange arguments video, I decided that split the sequence really deserves its own episode. And I really want to go in depth in that problem because it's a really interesting problem. I want to live code it. I want to talk about different approaches and incrementally get to better and better answers. But it does fit into this theme of exchange arguments. So I'm going to make that episode 15. So next week, I'm just going to completely work on that split the sequence problem. But I encourage you to give that problem a try during this next week and use some of the techniques we're going to learn here. See if you can find the greedy property and see if you can actually prove it. And I'll do the proof next week. But that's the plan for the next 2 episodes. And as always, if you want to write anything in the chat, please feel free. I'll be happy to check that from time to time, and I'll be answering any questions that come up. Or you could chat with your fellow viewers, and that's perfectly cool too. So the first thing I want to do is I want to talk about just how we deal with proving things if you have a greedy strategy showing that it's optimal. And we're not really going to work on a problem that's an exchange argument per se. I'm just going to talk about the idea of looking at your greedy solution relative to every other solution. So the first thing I'm going to do is I'm just going to pose a math problem for you all. And that math problem is you have some numbers a and b. You know they sum to n. So you have to pick 2 positive integers a and b that sum to n. And you'd like to maximize the product a times b. You look around this, think about it for a bit when you're working this kind of problem. If you want to maximize a times b, you want these to be integers. You could probably start to reason that this is going to be maximized when the numbers are as close together as possible. You could think of it as like if you have a perimeter on a rectangle, the perimeter to side length ratio, or perimeter to area ratio, is maximized when it's most like a circle, and that's certainly true. So we're not looking for like a calculus proof here or anything more complicated. I just want to show you one way to do this, like as a way to generalize every other solution. So I'll break this into 2 cases, one where n is even, one where n is odd. And I'll let you work out the n is odd case yourself. I'll just do the n is even case. So I'm going to just assume that n is even. And I want to show that if I make a equal to b equal to x, so make everything the same, which means that the number is going to be equal to 1/2, then it's better than every other possible solution that exists. So here's our solution. If you take a times b, because this is the objective function that we're trying to maximize, that's going to come out to x squared. All right. So that's one way we can maximize things. The second thing we can do is now characterize every other solution. So one trick I'm going to say is, without loss of generality, I'm going to say that a is the bigger of the two numbers. So I'll say a is x plus some delta, and then b is x minus some delta. And so if you fix what a is, you'll know what b is. And what this is basically allowing me to do is look at every other possible solution that exists for a and b that is a product and maximizes this. So I can get all other solutions by subbing in for delta. So all other solutions. And that's if I pick any delta that's greater than or equal to 1. So now I look at the solution for this new a times b. So that's going to be x plus delta. And it's going to be x minus delta. And I expand this out. What I get is x squared plus delta x minus delta x minus delta squared. Some things cancel. I get x squared minus delta squared. Well, I know delta squared is going to be a positive integer, so I know that this is less than x squared. And so what I basically just proved here is all other solutions are suboptimal to our solution. And that's the base idea when you're trying to deal with greedies, is what you want to do is you want to compare it to every other solution that exists. So you come up with a strategy, and you want to see if everything else is worse than that strategy. So this is a case for a mathematical problem. Let's go look at another property or problem that we can solve. So there's this idea of making change. So maybe you have some number like 1,000. So you have 1,000 in currency. Maybe you have some coins, coin denominations. So maybe these are coin denominations. What we want to do is we want to figure out what's the minimum number of coins, minimum number of each coins that sum to exactly 1,000. And for the most part, greedy doesn't work here. So one thing we could do is I could have some special, let's do it this way. So maybe I have 501 is a coin denomination. And then 499 is another coin denomination. And one coin denomination is 1. So what you'll see here is if I want to make coins, one way I could do that is 501 one time, and then 499 one coins. So this in no way minimizes the number of coins I get back. But a much better solution for this number would have been taking two numbers of 499 and then adding in two numbers of a single coin. And that would get me, only using 4 coins, I get 1,000 coins there. So this is kind of a classic problem. The greedy intuition for the solution is maybe take the largest coin first until you can't take it, take the next largest coin, and take the next one, and see if it sums to that exact value you were given. And you can see in this example, I could be very bad if I follow that greedy strategy. But certain coin denominations, greedy will work. And so that's what we're going to explore here, is I'm basically going to prove if you use the US coin denominations that you'll always end up getting an optimal strategy. And so if I take something here like 37, one way I can do this is I can have a 25-cent coin, so a quarter, 10-cent coin is a dime for us, and then 2 1-cent coins. and we come out to 37. And you can't do better than that. In fact, if you always follow this greedy strategy, it's always going to get you the minimum number of coins. So for this first technique, it's basically going to be a type of exchange argument. But specifically, what we're going to work on is this technique of probing. I call it probing. And so what you do is you want to know what characteristics the optimal solution has. You can probe it for optimal solutions, and you use this technique, a proof technique called proof by contradiction, in conjunction with probing. And you can basically figure out properties that the thing is going to have. So we have a few types of coins. And one of the things I might conjecture is like, oh, what's the maximum number of dimes I can have in an optimal solution? And if you play with this enough, you'll see that nothing is going to have more than 2 dimes. And so what we'll do is probe the optimal solution and say, what happens when we have 3 dimes? So if I have 3 or more dimes, then all I have to do is I can replace it with just a quarter and a 5-cent piece. Replace it with these 2 coins right here. It's better than a dime. So 2 dimes is the max number of dimes. What's the max number of nickels? So one thing I could do is I could suppose that there's 2 nickels. But then it ends up being that I could just replace it with a dime. So this is strictly better. So at most 1 nickel. And then at most 2 dimes. So this is a way of, I don't know what the optimal solution is, right? But I can basically look at the optimal solution and say, what if it had this characteristic? So I'm taking whatever the optimal solution is. It's arbitrary. I don't really care what it is. And I say, well, if it has 3 dimes, I can make it better. But you can't make the optimal solution better. That's the contradiction. So if it had 3 dimes, I could make it better. Thus, it's not the optimal solution. So the optimal solution doesn't have this property. It's basically what I'm doing here. I'll do another one. Suppose, let's find the maximum number of pennies we can have. So you're never going to have more than 4 pennies. So suppose we have 5 pennies, 5 1-cent coins. Then you just replace those pennies with a 5-cent coin. And then you have less coins. So you can have at most 4 pennies. Okay. And the last thing I want to show is that you can't have both 2 10-cent pieces and a 5-cent piece ever. You can't have these 2 things in conjunction. So you're either going to have just 2 10-cent pieces or just 2 5-cent pieces. But you can't have both. And so the way you do that is that you suppose that you have both. What you're left with is a 25-cent, an equivalent to a 25-cent piece, which is less coins. So we know some properties that the optimal solution has. The last thing is anything that's not quarters is going to sum to less than 24. So out of the 5s, the 10s, and the 1-cent coins, some combination of them sums to at most 24. This is pretty easy to do by cases. I take the maximum number of 10s. Now I can't have 5s. And I take the maximum number of 1-cent pieces. This sums to 24. The other case is I maximize the number of 5-cent coins, which means I can have at most 1 10-cent coin. And then pennies are not restricted. So I can have at most 19. And in either case, 24 is the most I can form without using a quarter. So it should become fairly obvious that I would like to maximize my uses of quarters in this answer. So this gives us a way of analyzing what the optimal solution looks like. So typically when I'm analyzing these things, I'll make two variables to talk about my two solutions. So one of them is O star. It's the optimal solution. And I don't really care what the optimal solution looks like. It's really arbitrary, but it's a way of comparing yourself to the optimal solution. Another way you can think of it is this is any solution. So if we're as good as any solution, then we're optimal. That's another way you could think of it. And then G is my greedy solution. And so your greedy solution is not arbitrary. You know exactly what your greedy solution is doing. And in our case, our greedy solution always has the maximum number of coins. So I never have to consider a case where if I'm at some coin right now, that the optimal solution has more coins of that type than me, if I'm the largest coin I'm currently processing. And so now what we can do, we can prove some things. So what I'm going to do is I'll say Q1 is the number of quarters in the optimal solution. And I'll say Q prime is the, I'll do it this way, number of quarters in our greedy solution. And now I'm going to compare them. Well, I don't actually have to handle this case because my greedy solution guarantees to have at least the optimal number of coins. So there are only two cases that this could be. Either they have the same number of quarters or the greedy solution takes a suboptimal number of quarters. So what we do is we say, suppose, I do a proof by contradiction here. Suppose the greedy or the optimal solution takes less quarters, and our contradiction is I can't replace them because I have at most 24 using the other coins. That was a property I proved through probing. So my only other option that can exist is the quarters are equal in size. So the optimal solution, I basically just proved that the optimal solution and the greedy solution both use the same number of quarters. The second thing I can do is say, let's say D is the number of dimes in O star. And I can say D prime is the number of dimes in G. And so what I'd like to do is I do the same thing again. I've already taken out the number of quarters. I have the same number of quarters. So I can't have more dimes in O star. So then I look at G. It either has the same number of dimes or less number of dimes. And so I'm going to probe it again with proof by a contradiction. I'm going to say, what happens when I end up having less dimes in the greedy solution? So if the greedy solution has less dimes, what I'm going to do is I'm going to probe it and see if it what happens when it has less dimes. Well, the dimes can only be replaced by nickels and pennies. And we proved that we can have at most one nickel and at most 4 pennies. So there's no way using the rest of my optimal solution that I can replace this dime. So that's a contradiction. So the two sizes have to be the same. So I find that case works out. I do the same thing again. I'm going to say, let's make n the number of nickels. And that's in the optimal solution. And then I'll say n prime is the number of nickels in G. So we've already shown that O star and G have the same number of quarters, same number of dimes. I'm going to show that they have the same number of nickels. So once again, I just assume that they have less nickels. Assume the optimal solution decides I'm going to take less nickels than the greedy solution. And then once again, I get into this case where They can't be replaced. And so the number of nickels clearly must be the same. And the only coin left is pennies, so the pennies must be the same. And so what I've shown is what the optimal solution is has to be exactly the same as our greedy solution. One neat property of this technique is you actually show that the optimal solution is unique, too. There can't be any other solution than something that has our same quantities here, which is kind of a neat extra consequence for this. So we did have, oh yeah. So I did make a mistake going way back. Should have paid a little more attention to the chat before we continue on. Oh, I already erased it. But before I was talking about 1,000, and I ended up getting 501 plus 499, and it actually ends up that being optimal if I take the largest ahead. Oops. But there are ways you can end up making a problem for yourself. So let's go back to the breaking the greedy. So I actually didn't break the greedy argument on the coin problem originally. So if I have 1,000 coins, and let's say my denominations are 700, and this time 498 and 2, and 1, then this would actually break that greedy coin change argument. So thanks for catching this. Just change 501 to 502, and the other way could stand. Yeah, that's exactly right. So one thing I could do is I could have 499 and 502, and then this would also break the greedy. And this would break the greedy very poorly. So nice catch, everyone. Glad you all are paying close attention to the live stream. So pretty good. So that's the greedy idea for coin changing. So this technique of probing, just going back to it, sometimes what I use this for is if I want to know a greedy property in my answer, so then I don't have to consider certain classes of cases. So even if it's not the optimal greedy, I could say that the optimal solution definitely has this property, and then I can use some other algorithm to like figure out how to satisfy the other properties that I don't know. So you're not always going to have like a greedy that uniquely determines the answer based on what your greedy spits out. But this technique of probing the optimal solution, saying like, what if the optimal solution had this property, and then getting some problem, is really useful for extracting certain types of properties. And I've certainly used it when writing problems for contests myself. So one of the problems I talked about in the blog, before we move on, is what was the property that allows you to use greedy for coin change? So basically, the property that allowed us to use the greedy for the coin change was I went through everything with using my greedy algorithm. So I basically figured out all these properties through probing. So there's no more than 2 dimes. There's no more than there's no more than 1 nickel. There's no more than 4 pennies. And there's no more than, you can't have 2 dimes and a nickel in the same coin change. These are all properties that I was able to probe about the optimal solution. So these are all properties that are going to help me in the proof of showing that my greedy solution is always the same as the optimal solution. It has to be the optimal solution. So the trick here was to extract this 24, showing that I can't do anything with quarters. The most I can sum to without quarters is 24. So I handled those 2 cases here. And so the proof that shows that the greedy is optimal is I take what the greedy solution is, because I know what it does. I know it maximizes the number of each coin as they go. And then I just show that in every single case, if the optimal solution takes less coins, then it's actually not the optimal solution because it doesn't meet the properties that I proved up here. So in this very first case, I showed, what happens if it takes less quarters? Well, the other coins can sum to at most 24, so it can't take less quarters. What happens if it takes less dimes in the optimal solution? Well, if it takes less dimes, this is the most it can sum to. It can sum to at most 9 cents using the other coins. And this property that it sums to at most 9 cents is just something I obtained through the probing based on the optimal solution. So I basically gathered a bunch of properties and then made this argument. The next one was I looked at the number of nickels. Said, what happens if I take less nickels than the greedy solution? Because the greedy solution is taking maximum number of nickels. And I end up with this problem, well, I can take at most 4 pennies. I have to replace the nickels I'm missing with some number of pennies. And then I replace it. I can't replace it because it won't be the optimal solution based on the probing. So then I'm left with the conclusion that the optimal solution must be exactly the same as the greedy solution. Sometimes you don't get something nice where you show that the optimal and greedy are exactly the same. Sometimes what you'll get is you'll get a solution that's equivalent in cost to the greedy solution through a series of exchanges. And so that's what we're going to see in this next example, is actually we're going to see something that is at least as good as the greedy that we're going to determine. Okay, so let's move on to this minimizing dot product problem. And this one comes from Google Code Jam from several years back. And it is a greedy problem. So here's how the problem is stated. You're given 2 vectors. Okay, and so what I can do is I can rearrange the components of these vectors so the dot product is minimized. That's what I want to do. So here are just 2 example vectors, but all I want to do is rearrange such that dot product is minimized. Okay, so let's look at the dot product. So I'm going to use indices to represent where I can hit in the vector. So here's my dot product. It's basically the sum of all the components. So if I have k components, I take vector 1 and I look at component I and I multiply it by vector 2's component I. And that's the dot product. So in this example, if I don't rearrange the components, I get -3 times 1, subtract 4, and I multiply it by 4. And so what I get left is -3, -16, 22, and 3. And so that's something that I can get for 3. So one of the things you'll notice about this version of the problem is I basically can list the numbers in the components. And I really care about pairing them up so that they get multiplied together. So in this case, I can pair -3 and -4 with 1 and 4, and 2 and 1. And if I pair those together, multiply them together, then sum their results. So I want to minimize this dot product by rearranging components. So it doesn't matter how I order each of these. One thing I can do is fix the ordering on the first one. So what I'll do is I'll just sort the first one by their components. And so now I have to come up with an optimal sorting of the second one to make the dot product minimized. One problem we have here is some of these values can be negative or positive. So you might start thinking maybe that matters. what do I want to multiply my 0 by? Maybe if I multiply a 0 by something else, that'll cancel something large out, things like that. But then you might start arguing something like, well, what if we match the largest things with the smallest things? And so if I match the largest things with the smallest things, what I get here is I get 3 times 11, negative 3 times 11. And then I multiply 2 times 1. And then I get negative 16. Here I get negative 47, multiplying these two components together. And that's much better than anything I've paired with so far. And so it seems like it worked in this case as far as getting something that is as negative as possible. But the big question we should be asking ourselves is, does this always work? And so the answer ends up being yes. It does always work. So then what we need to do is we need to prove it. So if we're looking at the two components, I'll say the first one is vector x. And so I can make the values be strictly increasing. And then for the y components, I sort them in non-decreasing order. And so if I just sort them in this way and multiply the components together and add them all, so you can try the problem in the blog, if you just do this, it ends up getting a correct answer. So what we're going to do is we're going to look at what happens if some I and j in this pairing does not meet this property. And if the I and j pairings somewhere in the list do not meet this property, what we're going to do is we're going to consider swapping them so that it gets closer to the sorted property. And that's what we're just going to explore here. So we're going to say xi is less than or equal to x of j for whatever I and j we pick. So we're picking an ij pair. So we know that this occurs because we determined that this would already be sorted. And we're just going to look at the case of what happens when yi is less than yj. Doesn't have the property. What happens after you swap them? And then all of a sudden you have the property. Well, at least for that pair. You might not have the property in general, but at least for that pair. So that's the first thing we're going to do. We're just going to look at a pair of items and see what happens if you swap one with the other. So here's the case in the current ordering. So I and j are the same component, or I is the same component, and j is the same component. So I want to multiply xi times yi and xj times yj. And then what I'm going to do is I'm going to subtract out what happens post-swap. And what this will do is it'll allow me to compare these two values pre and post swap. So my x's don't move, but my y's move. So they basically change what they pair up with. So now it just comes down to algebra. So I'm just going to distribute here. Something like that. Rework some things. So what I'll do is I'll factor out my x's here. So what I get is yi minus yj. So I factored out an x. And then I factor out a j. So I get yj minus yi. And I factored those two pieces out. But what I'd really like to do is I'd like to factor this and factor this because they almost look the same, but they're not really quite the same here. So I'll do x of I, yi minus yj plus x of j. I'm going to factor out a -1. So what I'll get is yi minus yj. So I basically just swapped these two locations and then factored out a -1. And so that allows me, so I basically get -yj plus yi, and then I rearrange the terms there. So now these two pieces are exactly the same, so I can factor them from each other. So what I get left is yi minus xj. So that's these two terms coming together to form that -xj. And then these two terms are exactly the same, so I'll get yi minus yj. And this is a really convenient form to be in because this piece right here is less than or equal to 0. And this piece right here is less than 0. So I basically have two negative numbers. Oh, well, this one's non-positive and this one's negative. So I know that this has to be greater than or equal to 0, which basically means for this pair that if this number is larger and I subtract it from this number, then this means that this is larger than this. So swapping is decreasing. Basically, when I swap these two values, I decrease my cost. All right, so what I'd like to do is I'd like to run my costs down going from one side to the other. So here's why this works. If you basically have your array without the swapping, so here's my y values. The idea is I can transform. I take something that doesn't meet the property that I care about, which was sorting it by increasing order. If it doesn't meet the property, what I can do is I can just start swapping values like back and forth, left and right. So in this case, I can swap these two. In this case, I can swap. Basically, if they don't meet the property, I can keep swapping them. And every time I perform a swap that's getting rid of one of these inversions, basically, or not inversions, depending on how you look at it, my cost decreases. So there's no way for me to get something that doesn't have that property to it either decreases or stays the same. So there's no way for me to get something that was optimal, like better than my greedy algorithm, and then through a series of swaps, get something that has a different cost. It's either going to be worse or it's going to be the same after a series of swaps. So basically, the argument there is your optimal solution, my greedy solution, is just as good as my optimal solution, looking at the final answer and then modifying it in this way. So really, when you do an exchange argument, is you just do a proof on the one exchange. And then you basically just have to argue that through a series of swaps from your optimal solution, through the series of exchanges, the cost is always staying the same or going down. And then you turn whatever the optimal solution is that maybe doesn't have the property that you imposed on the optimal greedy into the version that actually has the property you care about. And you've shown that that property is optimal. All right, so let's do like a high-level overview of what exchange arguments look like so far. So that I basically talked about it, but I just give a quick summary. Yikes. So what you do is you have a greedy solution that you'd like to characterize somehow. So you could look at it as a set theory kind of thing. So it's going to have some number of properties. And you have your optimal solution. We'll call this O star, and it also has some number of properties. So you're not really looking at the algorithm. You're not really running the algorithm. You're just looking at what the algorithm spits out. So this is what the greedy solution spits out, and this is what the optimal solution spits out in terms of its answer. So what we say is step 1, label the solutions. So I always label my optimal solution O star, and I always label my greedy solution G. So that's good. What's step 2? So step 2 is compare the two solutions. So what we're basically saying is, does there exist, typically what the properties you'll look at is you'll say, does there exist something in the optimal solution that's not in our greedy solution? Or does there exist something in our greedy solution that is not in our optimal solution? So you look for differences. And then you also, so maybe if I have a sequence, like so the optimal solution is some sequence, as we saw in the sequence problem. I say, well, if it's sorting by some property, so the most common thing to do with these exchange arguments is be sorted by some property here. You basically say, if it's not meeting my sorting property, then how does it change my answer? And so that's step 2, is you basically find some way of meeting the properties that you know the optimal, the greedy solution that you imposed have. So you know what your greedy is doing, so you know what properties the greedy solution has. And then step 3 is you exchange them. So here's what you do. You don't know what O star is, right? But you know it's a solution that has some properties. And you've made this exchange rule that's basically going to be able to walk you to the greedy solution. So the first thing I'm going to do is I'll make an exchange. And what I might get is another optimal solution, something that is less than or equal to the current optimal solution based on my exchange principle. In this case, maybe swapping 2 elements. We know that the cost goes down when you swap 2 elements that are out of order, or it stays the same. So then I go to O2. And through a change of exchanges, so I can basically do this a bunch of times till I get something that's O of n that has the same properties as my greedy solution. And if I do that, you'll notice this is always going down or staying the same. So it must be just as good as my greedy solution. The original O star and my greedy has to be at least as good as the original solution. And if that's the case, it's optimal, because I actually can't have this occurring for O star. So we know that for whatever objective we have for the greedy solution, and so I'm abusing equals here, but the score of this and the score of this are equal. It's basically all I'm showing. So you do that, you've basically proved an exchange works. Okay, let's try another problem that involves this greedy exchange argument idea. So if you look at SRM, and this is the one I'm going to live code actually, is SRM 502. If you look at div1, the medium, you can see this kind of really cool problem. So let's take a look at the problem. It's basically a problem on programming contest problems. So we have some number of problems that we want to solve in a programming contest, and the problems that we're trying to solve, you get some reward for solving the problem, so some number of points. So it's very much like code forces, actually. You get some initial reward for solving the problem. Then the award decays as you basically go down, and this is in per second. And then what we want to do is it also takes some amount of time to solve. Right, so those are the three properties for a problem. What I'm going to do is I'm going to make it a tuple. So there's the maximum number of points, how much does it decay per second, and how long does it take to solve? And that's what a problem looks like. So you're given some number of problems that you'd like to solve in this format. So maybe something has 250 points, it decays at 1 second, and it takes 10 seconds to solve. Where something has 500 points, it decays in 2 seconds, and then but it takes 1,000 minutes to solve. What you got to do is you have to figure out what order do I solve these problems, and which problems do I choose to solve, so that I end up getting the maximum reward. And you should notice that not all problems are worth solving. So some problem you might want to skip because the decay could just be really large. So if it was like 500 seconds here and the decay came out to 100, this would go really negative and you wouldn't be able to solve this problem. You'd actually get negative points for this problem. So it's not like Code Forces in that way. It doesn't have like a minimum for solving the problem. So let's talk about this problem here. Let's simplify the problem first. So sometimes when you're dealing with a hard problem like this, you want to bring it down to something a little bit simpler to solve. So here's my simplification. So we want to figure out which problems, let's say instead of knowing like if we're going to solve a problem or not, we want to know, what if we knew which problems we were going to solve? So instead of maybe choosing to solve problems or not solve problems, we just know upfront, hey, we want to solve everything. And so now what we need to do is we just need to find an order for solving the problems. So we only need to find the solve order. OK, so here's what you do. So I don't know what criteria I need to do to find the solve order, but I know that if there was some optimal ordering, then I could sort by this optimal ordering. But I don't know what this property is. So this is a really cool technique. What you can do is you can use the exchange argument to discover the property that you need to sort by. So I think that's kind of a neat thing to do. So here's my tip. If you think something has a greedy property to sort by, explore the cost exchange. When you change two orderings. So basically, when two problems swap, you just see what happens with the cost exchange. So in the first problem, we just guessed the sorting criteria. And this version, I don't know what the sorting criteria is up front, but I can explore it in the same manner. And then I'll actually figure out what the sorting criteria is. So what I'll do here is I'll make one is reward 1. So I have two problems, P1 versus P2. So reward 1 is going to just be the case where P1 comes first in this ordering. P1 comes before P2. So I'm only looking at adjacent orderings. So in that case, this is the maximum reward P1 can have. It pays some decay for the time it takes to solve. And then the second problem is M2, and it pays some decay because you have to solve both the problems before you end up using it. So that's reward 1. I get this equation right here. reward 2 is problem 2 comes first. So I get this minus T2. And so those are the two rewards. So what we'd like to do is we'd like to know the case where, because we want to maximize a reward, we'd like to know the case when is reward 1 better than reward 2? That's basically what we want to see. So one thing I can do is I can rework this cost and subtract reward 2 from reward 1. And it's greater than or equal to 0. Ends up being my optimal cost. So stuff gets shuffled around a bit. So now I can plug in for reward 1, reward 2, and start doing some algebra, at least hopefully. So what I'll do is I'll have M1 minus D1 T1, and then M2 minus D2 T1, and I'll distribute D2 here. And what I'll do is I'll subtract the other one. So I'm just going to subtract this whole piece, subbing in for reward 2. So I get M2, this becomes addition, this becomes subtraction, this becomes addition, and so on. So did I do that correctly? Oh, this becomes addition. Right. So you distribute the negative. So that becomes negative, positive, negative, positive, positive. Good. Okay, so things are going to start canceling here. So my M1s cancel. My M2s cancel. What else cancels? D1, T1 cancel. And these two cancel. So what I'm left with here is D1 T2 minus D2 T1. And if I rework this, I get, I can rework this several ways. I get D1 T2 is greater than or equal to D2 T1. So I want to know when this is greater than or equal to 0, essentially. Because if this is greater than or equal to 0, then I know that reward 1 was the larger reward. So this is me basically dealing with that reworked equation. So my sorting criteria is D2 T1 should be less than or equal to D1 T2. And I'm done. What this basically has told me in terms of my exchange argument is if I swap them according to when they don't satisfy this criteria. So in other words, if it's like this is the sorting I want to impose. If I do this, then I have an optimal ordering on my subproblems that I want to solve. Okay. So now we're getting somewhere in the solution, because now if we're going to take a problem, we have an optimal ordering for taking problems. So step 1 is sort by the optimal criteria. Okay. Step 2 is run dynamic programming. So the dynamic programming is basically just going to determine which problems to take. Because I know the optimal order, like once I know which problems to take, so I put everything in the optimal order, and then I just perform a knapsack style DP with recursive memoization. So that's basically what I want to do. So my state ends up being which problem I'm on and how much time I've used. And the transitions on this are either I solve the problem, I choose to solve problem, or I choose to skip problem. And then as long as I solve them in this order, then I know it's going to be the optimal order out of all the ones I can pick. And so that's how I solve it with dynamic programming. Okay, so let's go live code this one. I can show you how to solve this. So I'll be going into the Topcoder arena now. See if anyone else is also in the arena. I guess not. Although we do have Pablo still there. That's funny. Okay, so this is the amount of time you have a time constraint for the contest was part of the problem. So this is the time constraint. This is the maximum number of points that you can get. This is a decay, and that's the time it takes to solve the problem. So I'm going to make a problem class. And this is going to hold my information for the problem. So I'll be a bad mathematician type and use single variable names, just like I did in my notation. That's perfectly fine. So let's do comparison. So all I want to do here is I want to make a comparator. Basically tells me how I'm going to do the sorting. So the left side of my comparison is just basically going to be, so instead of doing a cast, I'm going to do 1L. But if you remember, my equation was the left-hand side was D2 times T1. And the right-hand side of my equation in terms of the sorting was D1 times T2. And so now I can use Java's utilities for this, for doing comparison. There are other ways to do it, of course. Right. So let's get some extra information here. So N will be the number of problems I have to process. T will be the max time I have. Let's make it an array for all our problems that we're solving in this programming contest. So Topcoder, I'll save the max number of things here. Save my max time that we have. Save the problem that I have. So array inputs are very inconvenient, but I can do a sort on everything like this. So I'll sort all the problems based on our criteria, and then I need to run my DP. So I'm going to do a memoized DP. I usually make a function called go when I do this. So once again, my state is how much time has gone on in the contest. That's T. I is like how many problems have I solved so far. I'll add the memo later. So if I'm on my last problem, I just want to return 0. let's figure out what the result should be. So there are two options I can do here. One, I can just choose not to solve the ith problem. And so the time doesn't change if I don't solve the ith problem. Otherwise, the time will change. So let's compute the time. So it's what time it is now versus how long did it take to solve that problem. And I should only consider solving a problem if it doesn't put me past the end time. So that's what I'm going to do here. And so how much reward do I get for solving a problem? I can basically use the formula in the problem, which is given to me right here. So it's max points minus the amount of time it is currently times the decay factor. So I'll do that decay factor here. So and so the reason I'm keeping it in longs is this time can be up to 10 to the 5th, and this value right here could be, the k value could be up to 10 to the 5th. So I'm worried about integer underflow, so I'm keeping it in longs. Of course, if the reward doesn't go below 0, then it's not going to underflow. So in this case, I can consider it an int still. So in this problem, you're asked to return an int, but your intermediate calculations can go below 0. So I'm worried about that kind of a bug. But now I can cast it back to an int. So what I do is I jump to the next time, jump to the next problem, and figure out what's the optimal number of problems I can solve remaining, plus this reward, I get RR. And then just save what's the best result between what's currently there and this. So there are really only two choices. This is the choice for not taking the problem. This is the choice for taking the problem in terms of our DP. And then I need to return the memoized version. So let's put in some memoization. That should be good. So if I'm in Java, one of the tricky things I do when I do memoized DP is I use an integer object, so I don't have to fill my memo table. And so originally, this 2D array ends up being filled with null. So I don't have to have like -1 as a special sentinel value if I haven't solved something. It just comes out as null. And so memoized DP, it always has this structure. Now I can check if the DP table is not null. Works great if you have negative values in your DP table and you don't know what value should be your sentinel value, or if you don't want to have an extra scene array. So that's basically how I deal with it. So I make a memo table like this, and that's my DP. So if you're not in Java, and you can figure out the C++ equivalent here. Great, so let's see if that works. Code compiled successfully. Let's run. Well, we passed samples. So let's figure, oh yeah, so let's try submitting it. So 469 points, submission successful. So let's see if we can run system tests. And correct. So not too bad on time either. So that's how you solve that problem. Basically, the programming contest div1. So it's an SRM 502 if you want to give it a try. And as I said, next week, what we're going to do is solve this problem, split the sequence. I think it's a really great problem if you haven't already solved it. It's pretty hard, but it combines some of the techniques we've talked about in previous weeks. And it also involves a really unusual exchange argument. It's not swapping two positions in an array. It's something else. So I'll be excited to talk about it next week, and that'll cover the whole episode. We'll just analyze that problem from top to bottom because I really think it's a beautiful problem and deserves its own episode. So thanks for tuning in, everyone. I hope you learned something today about exchange arguments, and definitely give that split the sequence problem a try. So I'll see you all next week.